Hey, hello YouTube players. It really is quite remarkable the amount of AI power that's available to the average person. The question is, what do you do with it all? You either contribute to something meaningful, like structural mechanics in FreeCAD, or you can turn yourself into the Terminator. I'm happy with my decision, don't judge me. Drafting or design? Technically, there's no upstream from design, but guess where the finger of blame lands if something goes wrong? The drafter's knowledge is a flow from design to manufacturing. So it's very important to be able to design before you accept the CAD position or have a clear clarification of that D word. We've all been there, right? Yeah, just keep making it stronger till it doesn't break. That's not computer aided design, that's computer aided destruction. When the economy of scale starts to include a risk to human life or a significant amount of time and money expense for R&D, then a design needs to be implemented. Some people will still say it's form over function, and good luck to those people. Structural mechanics investigates function via a load analysis, the strength of materials, a finite element analysis, a buckling analysis, and Chapter 1, static. Before we jump into Chapter 1 of Structural Mechanics and Intro for Technicians, I want to tell you, well, not so much about me, but more about the lecturers who taught me. Together, they designed this building among others, once known as the Sydney Centrepoint Tower, and for a long while it's been a big deal in our skyline. So they knew their business. When an engineering course starts, there's a 75% dropout rate, and even these lecturers aren't as focused as they should be, as there's good money to be made by betting on who's about to drop out and who's not. And without a decent library on these essential skills, the primary engineering subjects can be a little harder to learn than they should be. If it's not moving, it's static. If an object is moving, it's dynamic. Typically, buildings are static. So let's go ahead and take a component out of a building, say a truss. With this macro that I've wrote with the help of AI, there's a list of different types of trusses that you can use. And the span we're looking for isn't really that relevant at the moment. Neither is the height, neither is the members. But I do like to put it on the front. So we'll just preview this. Span of so many. Yep, that's better. And we'll commit that. Close. And the beauty of this for analysis is that when it's drawn, each section or element is individual. There's no continuation between the nodes, and this is important in 2D analysis such as structural tools. Now the first thing we want to do, if we just switch over to, actually I might just show you the example. It will be easier for me at least. So we have a load of 15 kilonewtons, and we can assume logically that each of the reactions is going to be equal or spread out over the two places where the truss touches the walls or the supports. But in a case where a truss might have an offset loading, the reactions will be different. And as you can see from the workings here, you can determine the loading on the support either by proportionality or a percentage of the load of the load, a percentage of the load relative to the span. So if this is over 25% of the span, then this will take up 75% of the load, and this one will take up 25% of the load. So it's really quite convenient, but in no way the entirety of the subject of statics. It is quite complex, and there are 4 basic force systems: coplanar, concurrent, coplanar, non-concurrent, and these 2 are basically software: non-coplanar, non-coplanar, concurrent, non-coplanar, non-concurrent. But without knowing these 2 in good detail, you really shouldn't be using software in the first place. So I've simplified this section with another macro, which I'm about to show you. But section 2, coplanar non-concurrent, it's all theory. And yes, structural analysis version 2, the one I've written, does have the tools to do this kind of work. But should you do it before you've done hand calcs? Because the idea of using software is to confirm your calculations are correct or within ballpark, so you then have some confidence. Coplanar concurrent force systems are simply a group of forces, so the green ones can be simplified into one force called the resultant, and it has a balancing force. So you can balance all these forces with one force. I guess it's probably best to show you an example. Here's one I prepared earlier, but I'll switch over to FreeCAD. Okay, so this is the macro, and if we use these forces, force 1 and pull off the front plane, we want 10 kilonewtons, the angle is 45, okay, so the scale 1 kilonewton equals 10 millimeters. The font size, I have no idea, I can't remember. Let's have a look what happens. Okay, I'll turn on the axes. And the second one is 20 kilonewtons at 90. So 20, 90. There we go. The third one is 10 kilonewtons at 120. Alright. And now we also have a spreadsheet. And so we can see the spreadsheet is there with all our forces. And if I zoom out a bit, you can see there's FX and FY there as well. Now, to get the resultant vector, we need to know the rows we're working with. 2 to 4. And we have the opportunity to exclude rows. And then we have it. And we can create an opposite resultant as well. This would have been a lot of trick otherwise. basically you got to break it all down into X components, cos and sine, and then to get the resultant you need tan. So yeah, the whole party. But this turns, say, a 20-minute problem into seconds. All the macros that I'm talking about will be included with the book. Shameless plug there. But if you're interested in structural mechanics or becoming a better designer, then I highly recommend having a read. I'm actually publishing this book chapter by chapter because, I don't know, it's a labor of love, I guess. So eventually it will be sold as one, but in the meantime, yeah, it's just plodding along. And if I can get the knowledge out there sooner rather than later, it's probably a good thing. Looking at exercise 12, we can see that the beam is 10 meters long with a 10 kilonewton upward force, 2 meters from the roller support on the left, and then a central 20 kilonewton downward load on the beam. Okay, so the loads aren't going through a central point, so it is a non-concurrent, coplanar non-concurrent. It's on one plane and there's a moment. So, well, there's 3 moments. If you take your equilibrium of moments about R1, let's do that. So minus 10 is, the minus is outside the bracket because the force and the distance create the moment, and the moment is either positive or negative. So that's why the value of the force is always going to be the nominal value, not a plus or minus inside the bracket. It's the moment. So we put all those in brackets. Plus 20 times 5, and then minus R2 because it's going up, times 10. We work out R2 to be 8, and at this point we could use either equilibrium of forces vertically or take moments about R2. That's a typo. Yeah. So let's change that. Let's fix there. So basically we're doing the same thing in reverse. Taking moments about R2. We've got 20 times 5. It's going anti-clockwise, so it's minus. Then we've got 10 times 8, which is positive because it's going clockwise. R1 is also positive because it's going clockwise, times 10, and we transpose that equation to get 2 kilonewtons. And if we just do a double check, the equilibrium of forces vertically, 0 is equal to 0, so it's statically confirmed. But we take this same problem, remember we got 2 and 8 on each of the reactions, and put it into commercial software. We've got a pin support there and a pin support there. It should really be pinned and rolled, but I don't have access to that. But we can see the difference. 10 and 4. Now let's change one of these over to fixed. We've got 13 and less than 1. Okay, so you can notice the difference that the type of support induces onto the system. I don't have access to Spring in this software, but what I am using it for is to just double check that we're on the right deflection scales, bending moments, etc. So shear forces, bending moments at 45, displacements at 17, bending stress. Okay, so we'll come back to that. Unfortunately, I drew this at 1 meter, not 10 meters. So I've got to draw another one. If you notice that we're in Structural Tools 02, it's been modified from the original Structural Tools. I take no credit in all of this. Some of it, yes, but not in all of it. Okay, so the first thing we need to do to simulate this beam is to get a line, and we'll start that at minus 5,000. Another point. And another point. There we go. There we go. Don't like errors. If there's ever an error that I can't explain, always delete refresh the console on the report view and hit F5. If the error doesn't repeat, you're good to go. Well, in my opinion, you can go back and chase it if you like, but this is FreeCAD and it is development software. Moving forward, so we have option. Now the first thing we need to do is to get a section for our beam. We don't know what section it is, we have to just guess. I'm going to do something quickly. It's called a macro loader. It just organizes my macros, and I now have a group of macros loaded. Doesn't really need to come over, but now if I open up my Australian steel, part of the steel collection, the I-beams at least, I can now choose from the grade and the available UBs. Okay, let's go with UB 310 UB40. Now on the top plane, basically you need a face. You need a face to assign it to this line, which will become the structural element. So that's why I have the shape binder included in the toolbar. You could effectively just shape bind a face to this line. I mean, shape bind a face into the document and then assign it to the element. But we need to assign the section, use that. So now in the properties, we can check all the values there. Because it doesn't have the fillets, it's not going to be exact, but the numbers are going to be pretty close. Alright, so we need a material that comes in as steel, and now we can assign the element. And you notice in the line section, 4 new properties have dropped in there, and we only need to change 2 of them. The material, okay, and the section. Now if it was a truss member, no bending forces can go into it because the ends are normally pinned. Perhaps for another time. Alright, so we don't need that. We can check it's been assigned properly. We can just view the section, hit F5. That looks good. That looks good. You also have the full beam there. We don't need either really, because they'll just impinge our progress. The next step is to have a restraint. That's a node restraint, this one, and this one is a variable restraint. So if I select the element, I can put the restraint anywhere on the beam, which is different to the original version of Structure Tools, where you're restricted to only nodes. And to change this, you get the idea. And you can also change the rotation, translation. But let's delete that. Moving forward, let's put another node there. This one has to be pinned, so I can rotate it in the Y. This one's roller, sorry. And it can transverse in X. That's why it's good to be in the front view. This one is pinned, so it can rotate in the Y. Alright. In the old version, we were restricted to only nodes on point loads on the nodes. Now we can use point loads anywhere on the element. It's already lined up the center, so we'll just change this over to 20. Looks good. Perhaps I need to put a commit button on that so you can keep it open while you're putting the data in. Alright, so there we have it. We should be good to go. The next step, Shift B, make sure you select everything and hit this button. Yeah. We won't include the self weight. I want to see the reactions. That's what I'm interested in, the reactions. Then we run the analysis. Cross our fingers. Completed successfully. Okay, and now we want to open up a diagram. The calc selected. Well, that's pretty close. Well, that's a home run. In structural mechanics, that's a home run. Okay. In the diagram, what I will show you though, the text. If you remember, we got 17. We're now at 16.6. So also another home run. 45 was the bending moment. Bending moment. We want the this guy. 39 kilonewtons. So in this instance, I'd probably be looking back at hand calc. 39 and 45. What's that? 6 kilonewtons. 6 divided by 45 is 13%. Probably a bit more than what I'd be comfortable with. I would want to try and keep my percentage error as low as possible, but that's why we have safety factors. But they're not extremely off, you know what I mean? I mean, that is a home run, in my opinion. And I will be testing the rest of my course notes against this and debugging it before it goes up for sale and published on YouTube. I do hope you consider to purchase the book